Hello and welcome to Crazy Math Productions. Today we're going to be looking at solving linear systems equations by graphing. We're also going to be looking at some special types of linear systems. Now, the point of all this, again, if we take a line, this line really isn't a line actually, but many dots, many small points. What's happening is that if you pick any of these points and plug them in to, let's say, y equals 3x plus 5, any given equation that you have, each one of these points, if you take the x and y coordinates and plug them in, will make them true. So each one of these little points, of course, granted, as I'm making it, it's not going to make a very straight line, but there's an infinite number of these little points or solutions that's actually going to compose that line. And when you put all of them together, that's actually what makes your line. So when we talk about a system of linear equations, what's going to happen is we're going to try to take two of these lines and we're going to look for what is a solution of both. Well, just a very simple exercise. Is this a solution to this line, this red point? Yes, because it lies on the line. Is this a solution to this line? Well, no, because it does not lie on the line. If it were plugged in, it would not make this true. So you notice the red is a solution, the green is not a solution. Well, that makes our job pretty easy when we're looking at a system. What we're going to know is what is a solution to the entire system. The red dot, the red point there, is a solution to this first line. The green is not a solution to either one. But the blue point, it lies on both lines at the same time. And that's exactly what we're looking for. So a solution to the system, well, that's basically going to be the point that can satisfy both equations at the same time. You could do this several ways. We could do it graphically, which is what we're going to do today. You could do it algebraically, which we're going to do soon, two different ways, one by combination and one by substitution. And so we have this this new way of looking at a system instead of just an individual equation. Now, we also could have some different things to happen. What happens if our lines are like so? Now, the red is a solution to the upper line. The green is a solution to the lower line. What if these two lines were parallel? What would be the solution to the system? Where's this blue dot going to be? Well, you're never going to be able to put it. There's not going to be a solution. There is no real solution here. So if that happens, you literally put no real solution. Now, occasionally, these two lines will actually be versions of each other. So the red point is a solution. The green point is a solution. The blue point is a solution. It doesn't matter where you go. There's an infinite number of solutions. So as you go through with lines, you're going to have several options. You could either have one solution, which we had earlier, where the blue point was the solution. There was only one solution. You could have no solution, where they're parallel, or you could have infinitely many solutions, where they're literally the same line. So keep that in mind as we go through the lesson. Okay, determine if the given point is a solution of the system of linear equations. Well, what I like to do, I like to color code the different lines. It helps us to keep them straight. It can be confusing sometimes. So we have x and y, and all we're going to do, see if it's a solution. Well, remember that a solution is going to be something that's going to plug into both of them and make them true. So what I'm going to do is to plug in 3 for x in the red. First, I'm going to do the red on the left side here so we can have some clarity, know what's going on. Plug in 3 for x, so this is 2 onto 3, plus 3 onto y is 2, equals 12. So again, I'm just putting, instead of the x, I'm putting a 3. instead of the y, I'm putting a 2. And so I'm plugging these in. That's all I'm doing. 2 times 3 is 6, plus 2 times 3 is 6 equals 12. Is that the case? Well, 6 plus 6 is 12. That checks out. So it's a solution to one of them. But again, we're talking about the system, so it must be a solution to both of them. So let's try out the blue line. Plug in 3. Minus 4 times y is 2 equals negative 5. Negative 4 times 2 is going to be negative 8. Again, I'm just going to put a little question mark here just to say that I don't know whether it is or not. 3 minus 8 is negative 5. So yes, that works. Since it works in both of the lines, it works in the entire system. Now what if there were 3 equations? Well, you'd have to try it for all 3. It must work for all 3 as well. So determine if it is a solution. Yes, it is a solution. Okay, let's continue. Number 2, same kind of a deal. We're going to try the red and the blue. I'm going to color code them so it's easier to work with. Okay, let's try the red now. 3 times, see, x and y. 3 times 3 minus 2 times 2 equals 0. 3 times 3, 9 minus 4 equals 0. A little question mark. 9 minus 4 is 5. Now, is this true? Well, no, it's not. 5 is not equal to 0. So I can immediately, I don't have to look. It has to be a solution to all of them. If it's not a solution to one part, you don't have to continue. You do not have to continue. So no, it is not a solution. All right, now that we understand the concept of a solution or not a solution algebraically, let's look at it graphically. Now, if you have some different colored pens, I highly recommend, I'm going to use red and blue. I may need to pause the video and run get a pen. And we're going to look at these two. Now, these happen to be in slope-intercept form. Very nice, very convenient. So we're going to go ahead and start. A reminder that we need them in slope-intercept form for probably what is the most convenient way of graphing. We're going to use the slope-intercept form. Again, you start with, if you follow Crazy Math Productions, we affectionately call this Moby and the boat. Of course, it's actually the slope and the y-intercept. B for the boat, that is the y-intercept. Since it's the y-intercept, we start on the y-axis. So, y equals 2x minus 1. Negative 1 is the y-intercept. That's the boat. We start off on the y-axis going down 2, since it's negative 2. Now, I don't see an obvious rise and run for my slope. 2 is my slope. So I'm just going to simply put the 2 over 1, rationalize this. And now that we have 2 over 1, we're going to rise and run, rise 2, from my y-intercept, and run 1. Rise 2, run 1. And I'm going to continue this. I'm also going to continue in the opposite direction. Now, I'm not going to put my line yet. Now, why is that? Technically, it only takes 2 points to determine a line. But you notice, I could make this line, let's look at these 2 dots here in the middle. If I were to graph my line, you kind of notice this line, I can make it appear to be over these 2 points, but really, if you look down at this end, there's a huge range of where this line goes. Now, that's only if I have those 2 points. Now, if I extend it all the way, you can see that this is probably not the most accurate. This is also not. This one kind of fits with the general trend of the points. So the more points there are, the better of an understanding I see of where exactly this line is really supposed to go. You can sort of think of it as if you've ever seen a sawed-off shotgun, the reason is it spreads very quickly, and the shorter the barrel is, the less accurate. Well, you don't want it to be accurate, you want it to spread. If you've seen, say, a rifle or something like that, it has a very long barrel, and the reason for that long barrel is that it's much more accurate for some different reasons, but the point is that the longer the barrel there, then the more accurate, generally speaking. So if we have this longer barrel here, then we're going to be able to see exactly where the line is. Now, you may have noticed we spent a lot of time talking about why we need this to be very accurate. Well, suffice to say, put down as many points as you can on the graph that you're given, or you can create your own, of course. But we're trying to keep it as accurate as possible, and I'm not going to graph that line yet. Now let's go to the blue line. Y equals 1/3 x plus 4. Now we're going to go up 4, that's my y-intercept. Place the point. I'm going to rise 1 and run 3. Now, if you remember from above, I'm looking for the place where it's a solution to both at the same time. Well, there's my intersection right here. It's the point 1, 2, 3, 1, 2, 3, 4, 5. Well, guess what? That's the solution to the entire thing. Now, it's a little tacky just to leave it as this, so I'm going to go ahead and go back and graph it. But you notice it's helped that I had just the points there because I was able to determine that point immediately. There's a little extra work on the red to go ahead and put it all the way across the graph, but it made the job a little easier because now I simply find the point of intersection. I know what my solution is to the system, and then I can go back and put my lines. It just makes the job a little easier. A little bit extra time, but it's well worth it. Okay, let's look at number 4 here. All right, now this is, I'll declare to be the red. This is the blue. Now I need to solve each one of these for slope-intercept form, y equals mx plus b. 2x plus 3y equals -3. I'm going to subtract 2x from both sides. Divide by 3. And y equals -2/3 x minus 1. Now you notice this negative is out front. I'd really prefer it to be either on top or on the bottom, which I'm allowed to do because it doesn't matter whether it's just -2/3, -2 divided by +3, or +2 divided by -3. They're all the same thing. So just for convenience sake, I'm going to move the negative to the top. Doesn't change anything, but it makes it a little easier to graph. And we'll try the same thing with the blue line. We're going to keep change. Excuse me. That's a -1y. I can put the 1 just to make it a little more convenient for myself. Subtract x from both sides. Remember that was a +11 over here. Okay, now we need to get rid of this negative. We need it to be positive y equals mx plus b. So we'll divide by -1. Y equals +1x. 11 divided by -1 is a negative. 1 divided by 1. Y equals 1 divided by 1x minus 11. And the reason that I made this fraction here is so that I can see distinct rise and run with the x there, the slope. Okay, I have 2 equations. I'm ready to go. Let's go ahead and get it done. The y-intercept is -1. Go down, plot point. Rise -2, run +3. And again, from the earlier one, I want to go as far as I can either side and plot these points, but don't graph the line yet. Now here, you notice if I put the negative in the bottom, I could rise a +2 and run a -3. And you see it gives me the same sloped line. Okay, so I'm done with the red. I'll need to go back and graph the line later, but for the moment, that will do. Now, y equals 1 over 1x, 1 first x minus 11. I'm going to go off the graph just a little bit for this. And there we go. I'll sort of plot my own um, Cartesian extension here. And now we're going to rise one, run one. That's why these tick marks are so important. You can't just guess, because we're going to use those to make sure we stay on track. Aha! Found it. This is my solution to the system of linear equations. Just going to jot that down real quick. Let's see, 1, 2, 3, 4, 5, 6. Negative 1, 2, 3, 4, 5. And that's it. Now, again, it's a little rude to leave it this way. It's a little tacky looking. So we're going to go ahead and complete by graphing those lines. And there we go. A few more and we'll call it a day. Alrighty. Call this one red and blue. I would strongly encourage you, go ahead and stop the video and see if you can do it on your own. Okay. Solve for y. We're going to subtract 2x from both sides. Divide by 3. And y equals negative 2 thirds x plus 4. Notice, just by way of habit, I've put the negative in the top, just for the sake of convenience. Also, with the blue, in this one, I'm going to subtract x from both sides as well. Divide by negative 3. And y equals negative divided by a negative is a positive. Now I'm going to put a 1 here and pull the x out back so that I have a positive 1/3 x. Negative divided by negative is a positive. And here we go. In this case, we're going to go ahead and start with the red, as usual. Start at the y-intercept. We're going to go up 4. 1, 2, 3, 4. Rise negative 2, run positive 3. Again, from the y-intercept. Go both ways as far as we can. And I'll start with the blue. Rise positive 4. Oh, there it is. Now, I can't just leave one dot. I do need to graph the line, so we'll go ahead and put one more. Rise 1, run 3. And that's pretty much all I need. I could continue it both ways. Would be nice. But now that I've actually found that point of intersection, it's not really necessary. So make sure that you tell the actual point of intersection, the solution to the system, 0, 1, 2, 3, 4. Alrighty, let's continue. Again, I would encourage you, I'm going to make this my red line and my blue line. I would strongly encourage you, go ahead and pause the video, see if you can do it on your own. Let's see how you did. We're going to go ahead and divide everything by 3 here. And it's ready to roll. Let's try with the blue. Again, divide everything by 3. Y equals 5/3 x plus 2. Okay, let's go ahead and graph each one of these. We're going to go down 1, rise 2, run 3. Continue that for as long as we can. Now let's start with the blue and see if we can find that point of intersection. We're going to rise 2, plot the point, that is the y-intercept. Rise 5, run 3. Now you may notice, are we getting closer or further away? We're getting further away the further to the right we go. So we'll definitely need to go back the other direction to find that point of location, that point of intersection, excuse me, the solution of the system. So we're going to go down 5 and left 3. And there's my point of intersection. Alrighty, number 7. Red, blue. Again, I'd encourage you to stop the video and try to see if you can do it on your own. Let's see how you did. I'm going to subtract 5y from both sides, subtract 3x from both sides at the same time if I can. So we have negative 5y equals negative 3x minus 10. Divide by negative 5. And y equals negative divided by negative is a positive 3/5. X, negative divided by negative is a positive 2. Now let's try the blue. Add 3x to both sides. We have 5y equals 3x minus 15. Divide by 5. Y equals 3/5 x minus 3. And now let's graph these. With the red one, we're going to go up 2 to the y-intercept. We're going to rise 3, run 5. And go the other way. Went up 3 into the right 5. Now we're going to go down 3 and to the left 5. Okay, now let's try to find that point of intersection. Go down 3. We're going to rise 3, run 5. Doesn't seem to be getting closer there. Go down 3, left 5. Now, do we seem to be getting closer or further away? Well, actually, neither. If you notice, if you had a keen eye, you'd be able to notice immediately 3/5 and 3/5. They're actually the same slope. Same slope, different intercepts. That means that these are parallel lines. If they're parallel lines, you're never going to find any point of intersection. So what is my solution? There is no solution. Now, in this class, in this course, algebra, we're going to be working algebra 1 anyway, only in the real number system. So just to play it safe, we're to say no real solution. And there we go. So try number 8. Again, I encourage you to try it on your own, although you may be a bit confused. Go ahead and try it, and then we'll see how you did. Okay. Again, let's go ahead and solve. Make this the red, and this is as the blue. as traditionally we have done. Let's solve for y here. I'm actually going to add y to both sides, then subtract 2x. Y equals negative 2x plus 4. Then the blue, I'm going to subtract 6x from both sides, divide by 3, and y equals negative 2x plus 4. Got a keen eye, you'll notice. Slope, same. Oh, so they must be parallel. Well, not really, because the y-intercepts are also the same. That means that these are the exact same line. Now, I'll go ahead and graph it to show you what I mean. The y-intercept is positive 4, rise negative 2, run positive 1. Let's do that with the blue as well. We're going to go up 4, y-intercept, rise negative 2, run positive 1. Now, the intersection, well, quite frankly, it's everywhere. It's exactly the same line. So there's an infinite number of solutions. We're going to say there are infinitely many solutions. And that will do it for today. Thank you so much for watching Crazy Math Productions.